Hi, today's video involves continuity. First, let's remind you of the definition of continuity. A function f of x is continuous at x equal a if the limit as x approaches a of f of x is equal to f of a. You can think of this in three parts. The limit as x approaches a of f of x exists. 2, f of a is defined. And 3, these are the same. Okay, we talked about some existence of issues with limits before. So this is how we have continuity. Remember, for the limit to exist, often you must consider one-sided limits. So often this gets broken down a little bit further. We need the limit as x approaches a from the left of f of x to equal the limit as x approaches a from the right of f of x to be f of a. All three of these things have to happen. With that in mind, let's look at some problems. So, first, I want to find little a and little b so that f of x equals piecewise defined function a times 2 to the x plus 3x plus 1 if x is less than 2, and x squared plus ax minus 5 if x is greater than 2, and b if x equals 2. Find a and b so that this function is continuous everywhere. Okay, first, the only issue with this function is going to be at x equals 2. Everywhere else, an exponential function is continuous everywhere, polynomials are continuous everywhere. The only problem is x equals 2. So, we need to make sure that the limit from the left as x approaches 2 is equal to the limit from the right, and then define the value for b to be that limit. So, the limit as x approaches 2 from the left, a times 2 to the x plus 3x plus 1 is equal to 4a plus 6 plus 1, or 4a plus 7. The limit as x approaches 2 from the right of x squared plus ax minus 5 is equal to 4 plus 2a minus 5, which is 2a minus 1. To be continuous, we need then 4a plus 7 to equal 2a minus 1, which means 2a is equal to negative 8, so a would equal negative 4. That being said, then either of these one-sided limits the limit as x approaches 2 of f of x is going to be, we can put in a equals -4 in either one of these. Notice -16 plus 7 is -9, -8 minus 1 is -9. And so this has to be my value for b. So b is -9. Okay? My second problem that I want to look at is, let's erase this. Determine where f of x is discontinuous and the type of discontinuity. Remember, we looked at 3 different types of discontinuity. There are others, but 3 main types of discontinuity that we considered: removable, jump, or infinite. These are the main types of discontinuity. So, removable, let me limit as x approaches a of f of x exists, but it's still discontinuous. Jump, the limit as x approaches a from the left does not equal the limit as x approaches a from the right, but they're both real. And infinite, the limit as x approaches a from the left is some kind of infinity, or the limit as x approaches a from the right is infinite. Those are how we define or determine which type of discontinuity that we have. Okay, so let me erase this. I can use the board. And let's suppose we have the following. F of x is equal to 3x plus 2 if x is less than 2 and x squared minus 4 over x squared minus 4x plus 4 if x is greater than 2. Actually, this first one should be less than or equal to 2. Okay, so we'll look at, again, the only place we have issues is at x equal 2. The limit as x approaches 2 from the left. We're dealing with the function 3x plus 2, and so that value is 8. The limit as x approaches 2 from the right. In this case, I am using the function x squared minus 4 over x squared minus 4x plus 4. This is indeterminate. So I have to do some more work. We saw these. This comes out to be x minus 2 over x times x plus 2 over, my denominator is x minus 2 squared, or x minus 2 times x minus 2. And so we end up with limit x approaches 2 from the right of x plus 2 over x minus 2. And notice now this is no longer indeterminate. My numerator is approaching 4, my denominator is approaching 0, which means we get an infinite limit. And since my limit from the right is infinite, in this case, we have an infinite discontinuity. Doesn't really matter that the limit from the left is a real number. Limit from the right is infinite. I don't really need to even figure out which infinite it is. I don't care about that. All I care about is the fact that it is infinite. Hence, we get an infinite discontinuity in this case. My third example, again, is worked out for you. It is problem 6. And again, it's a piecewise defined function. F of x is, this is need a little bit more room. X minus 5 over x minus 7 if x is less than or equal to 1. The square root of 8x plus 1 minus 3 over x squared minus 1 if 1 is less than x is less than 3 and x squared minus 4x plus 3 over x cubed minus 4x plus 5 if x is greater than or equal to 3. In this case, I have two different values I have to be concerned about, x equal 1 and x equal 3. Everything else is not a problem. So, first off, when x equals 1, the limit as x approaches 1 from the left. This is simple. In this case, my function is x minus 5 over x minus 7. And so this limit then comes out to be negative 4 over negative 6, which is 2/3. The limit as x approaches 1 from the right. In this case, I need to be consider values that are larger than 1, but close to 1. So I'm going to be dealing with this middle rule, square root of 8x plus 1 minus 3 over x squared minus 1. This is indeterminate. So I will have to do like you saw previously. We'll multiply by the conjugate. I will go through this a little bit quicker. I did with the other one. Multiply by the square root of 8x plus 1 plus 3 over the square root of 8x plus 1 plus 3, which then gives us 8x plus 1 minus 9. Oops. Drop my limit. Over, I'll factor x minus 1, x plus 1, and we still have this other factor, the square root of 8x plus 1 plus 3. My numerator becomes 8x minus 8, and so I'm going to just work with that and factor out the 8. And I'm left with x minus 1. My denominator is already factored. And we'll reduce. I end up with 8 over x plus 1 times square root of 8x plus 1 plus 3, which finally gives us 8 over 2 times, as x approaches 1, this approaches 6, and so this becomes 8 over 12, which is 2/3. So notice, the limit as x approaches 1 from the left was 2/3. The limit as x approaches 1 from the right was 2/3. The function is defined by the value that we had from when x is equal to 1. And so therefore, this function is continuous. At x equal 1. So we do not have a discontinuity. The two pieces match up. They line up. We still have to deal with x equals 3. So I am out of room. I'm going to have to erase all this, but just remember, this is continuous at x equal 1. Now let's consider x equal 3. And then we have to do exactly the same deal. The limit as x approaches 3 from the left. Now I'm dealing with values that are less than 3, and I'm using the middle rule. Square root of 8x plus 1 minus 3 over x squared minus 1. In this case, this is not indeterminate, however. So we can just go ahead and evaluate it as it is. This becomes 5 minus 3, which is 2, over 9 minus 1, which is 8, or, oops, don't need that, I'm evaluating, and so this becomes 1/4. On the right, the limit as x approaches 3 from the right. Now I am using the third part of my function, x squared minus 4x plus 3 over x cubed minus 4x plus 5. This denominator does not approach 0. 27 minus 12 plus 5. So again, this is not a problem. It's not an indeterminate. It's not infinite. We can just go ahead and evaluate it. My numerator, however, is 0. The bottom, the denominator, let's see, 27 minus 12 is 15 plus 5 is 20, or this comes out to be 0. So in this case, the limit from the left was 1/4, the limit from the right was 0, therefore, the limit did not exist. Not that we're really asked that, but I'm just saying. And since each of these are real numbers, we have a jump discontinuity at x equals 3.